Hello and welcome back to quantum physics. Today we're going to do three things. We're going to introduce the idea of the state of a system. Physical things exist independently of how we choose to describe them. When we speak of the state of a system, we're speaking of that in a representation-free way. In other words, you could describe that quantum system any way. When we speak of the state of the system, when we write it like this, and more about that notation soon, we're speaking about the system in a representation-free way. This stick of chalk exists independently of whatever mathematical physics I use to describe it or whatever formalism I use to describe it. I could describe this physical system infinitely many different ways. I could describe an electron, for example, in a hydrogen atom infinitely many different ways. There are infinitely many ways to do quantum physics. And when we write down this, we're saying this is the state of the system in the so-called representation-free way. More about that later. We'll revisit operators again, and lastly the concept of eigenfunction expansions. The context here is the current chapter, which is chapter 5, called formalism, where we can render more precise. Now that we've got quite a lot of quantum mechanics under our belt, we can develop a more formal structure for quantum physics, which we'll use for the remainder of the course. So let's jump into this question of the state of the system. Again, what we're doing here is developing a formalism for quantum physics, the centerpiece of which will be a series of postulates, a series of 6 postulates, informed by experiment, but whose ultimate justification lies in whether or not the predictions, the associated predictions, agree with experiment. So what do we mean by the state of a system? Let me ask that question twice. Once for a classical system of n point particles, and secondly I'll ask the question, what do we mean by the state of the system for a system of a quantum mechanical system of n particles? If we have n particles in a classical system, n equals 1 is the first particle, 2 is the second particle, and so on, all the way up to the nth particle, the capital nth particle. If I was to tell you the position relative to some coordinate system O, if I was to tell you the position R1 of the first particle and the momentum P1 of the first particle, and similarly R2, P2, R3, P3, etc. If I was to tell you the position Rj and the momentum Pj for every single one, for every single member, j equals 1 through capital N, of an n-particle system, an n-point particle system, then I would have completely specified the state of that classical system of capital N particles. And at the risk of stating the obvious, this is the state. You've got strong knowledge. You know exactly what these n particles are doing because you've told me where they are, where each particle is, and how fast each particle is moving at a particular instant of time. By the way, we would speak of these variables, positions and momenta of each of our capital N particles, as dynamical variables. So these are spoken of as dynamical variables because they're variables that tell you the state of this dynamical system. How do we now specify this system quantum mechanically? We can't tell you the position and the momentum anymore, for at least 2 reasons. First of all, each of these particles may be in some sense a wave packet, and so it doesn't have a well-defined position. It may have an expectation value of position. Secondly, position and momentum are complementary variables. We have a position-momentum uncertainty principle, and so these things cannot be specified with arbitrary precision. So what do you mean by the state of the system? You can't tell me now where every particle is and exactly what its momentum is anymore. Can we specify the state of the system? Well, no, not in the strong sense of the classical term, but you can still ask the question, how do I give you as much information as I possibly could about the state of the system? And the answer is, tell me the wave function. If it's a quantum system, then you tell me the wave function, and that tells me as much as I could know about the system. It's not the total knowledge, the absolute totalizing knowledge of classical mechanics, which tells you where the particle is at each point, at each instant of time, where each particle is. Instead, it tells you something weaker to do with probabilities in accord with the Born interpretation. But that doesn't change the fact that in a quantum system, this gives you maximal knowledge of the system. You tell me the wave function, and you will know all that you could know about that quantum system. Now, if I had an n-particle system, what would that wave function be a function of? It would be a function of the position of the first particle, the position of the second particle, all the way up through to the position of the nth particle and time. So this would be the wave function for a system consisting of capital N particles. Now, the majority of this course is interested in wave functions in which there's one particle present. This will be the only class where I talk about so-called many-body wave functions. This is a many-body wave function because it's a wave function for many bodies. So what I've just said provides context. For the first of 6 postulates that we'll introduce today. So this is the first of 6 postulates that we'll introduce today. Postulate number 1, one can in principle associate with a given quantum system a wave function psi that captures all that is knowable about a quantum system. So this is the first of our 6 postulates to be developed in today's class. I mentioned earlier that this thing is to be interpreted probabilistically. So when we had a one-particle wave function, we had a probability density rho as a function of one position variable in time, which is the magnitude squared of the wave function, a single body wave function. And the interpretation of this was, at some instant of time t, you have some position vector r, this position vector r, and this particular time t, that this object, this is a probability density, a probability per unit volume. You multiply it by the infinitesimal volume dr, which is dx dy dz, the scalar dx dy dz, the volume of this box, located at position r relative to this origin O. This is the probability that at time t, you will find the electron at position vector r somewhere within this box. Now we're going to have a many-body wave function, psi of R1, R2, R3, etc. And it's going to have an associated probability density, psi of R1, R2, all the way up to Rn t, which is the magnitude squared of capital psi at the top of the middle board. What's this thing going to mean? Well, if I multiply it by dr1, dr2, etc., all the way up to drn. Now, dr1 is the volume of a first box for the first particle. dr2 is the volume of the second box, and so on, all the way up to psi n. We're going to have a position vector r1 for the first particle, r2 for the second, all the way up to rn. And this object here is going to be the probability that at time t, you find the first electron in this box, the second electron in this box, the third electron in this box, and so on. And this is a generalization to many-body wave functions of the Born interpretation. Now, the subject of many-body theory, more precisely many-body quantum theory, but it just tends to be called many-body theory, hugely important in quantum field theory, hugely important in standard model of particle physics, hugely important, particularly so in condensed matter physics. We won't speak about many-body theory again. Single-body quantum mechanics is rich enough and hard enough, but I just want to make the point that you can write down Schrodinger equations for n-particle systems. They're typically, by the way, impossible to solve and must be solved typically computationally. Our second postulate now is that quantum mechanical states obey the superposition principle. I won't say any more about that because we've met this before. Yep. I now want to introduce what's called Dirac notation. And I want to say also that almost everything that I write on the board for the rest of today's lecture is mathematics rather than quantum physics per se. There's a lot to be said about marrying the theory of functions, which obey linear differential equations, with ideas of linear algebra. Functions get acted upon by linear operators, which obey linear differential equations. Vectors get acted upon by matrices, which obey systems of linear equations. Setting up a correspondence between these two things is the essence of what we're doing now. That's a topic of functional analysis, an area of mathematics, but we're using it here for quantum physics. So as one example, the idea of a dot product of two vectors. You give me two vectors, dot product, and you can give me a number, which is the dot product or the inner product of two vectors. Can you do the same thing for two functions, let's say f and g? Can you have an inner product of those? I mean, the vector is just a bunch of numbers, and this is another bunch of numbers, and you multiply them together in some way, and you get a single number. Well, the function is a bunch of numbers. Two functions is two bunches of numbers. Okay, these are a countable finite set of numbers. F of x and g of x is infinitely many numbers, but the point is, two vectors can have a number associated with them, the inner product. Two functions can have a number associated with them, which is also called an inner product. In quantum mechanics, we'll use angular brackets. And this idea of getting a number out of two functions, which is the function equivalent of inner product or dot product, is what Dirac notation is about. So I'll move this out of the way. Is that all right? So let's introduce this Dirac notation. It's a way of taking two functions. Now, since this is quantum mechanics, let those functions be wave functions, arbitrary wave functions psi1 and psi2. So arbitrary wave functions psi1 and psi2. I'm going to integrate over all space, psi1 star, psi2. And this is going to be the inner product or the Dirac product of two functions psi1 and psi2. So this is the Dirac notation. Again, think about the parallels between what we're doing here and linear algebra, because the parallels are very strong. So with this definition of the Dirac bracket, so this is given a name, it's called the Dirac bracket. But it's nothing more than an inner product, the function equivalent of a dot product. You can prove three identities. If you take the inner product of two wave functions in a given order, or if you take them in the opposite order, these are related by complex conjugation. If you just stick some complex number little c inside the first slot, remember that first slot is starred, then if you pull it out the front, it gets complex conjugated. And the third rule, if you now have three arbitrary wave functions, psi1, 2 and 3, then their inner product will be the inner product of the first function with the first member of the right slot plus the inner product of the first function with the second member of the right slot. And we put a vertical line here rather than a comma because we want it to look somehow different. But again, I want to emphasize this is mathematics applied to quantum physics, or ultimately applied to quantum physics. Again, pushing forward this analogy, the dot product of two vectors, if it vanishes, we would speak of that, those vectors as being orthogonal. Exactly the same thing here. If the Dirac bracket of two functions vanishes, this is equation 132 in the notes. If the Dirac bracket of two functions vanishes, we would speak of these functions using deliberately geometrical language. We would speak of these functions as being orthogonal. The normalization condition can just be written in Dirac notation as the inner product of a wave function with itself equaling 1. Now, these things are given a peculiar name. It took me 4 years to work the following out. Dirac called these things a bra, and this thing a ket. We just use these words, bra and ket. The reason he chose these words is because together they make a bracket, and this is the first half of the word bracket, this is the second half of the word bracket. The most stupid notation you'll ever see. There's also a very deep thing which I'm hiding here. The concept of a dual space. In the theory of linear algebra and the spectral theory of operators, beautiful theory, you should learn it, these objects live in a particular space, a particular function space, and these things live in what's called a dual space. The bras are actually geometrically different objects to the kets. If you want to study the theory of dual spaces, please go for it, it's beautiful, but I won't be covering that here. I just want to make the point that I'm hiding some deep and beautiful mathematics here, because I don't want to go into the idea of a dual space. If you want to find out more about this, I recommend the book by Toshio Kato, and it's called Perturbation Theory for Linear Operators. Perturbation Theory for Linear Operators, which will explain the idea of a dual space beautifully. And that's a mathematics book again, not a quantum book. That's all I wanted to say about section 21. Let's move on to section 22, which is about our operators revisited. So operators revisited. So we had this idea of a linear operator. Now we've used linear operators before. You give me the wave function. I'm now going to represent it as a ket. And this is a representation free. I'm not stooping to a particular representation yet. You have some linear operator A, script A, so some linear operator Roman A, from which you can extract the dynamical variable script A. So as an example, this might be the wave function in the wave mechanics representation, capital psi of RT. This might be the momentum operator from the Schrödinger correspondence rules, which you use to extract the expectation value of momentum from some wave function. But we want to render this stuff more precise. And before I do so, I want to revise the idea of an eigenfunction and eigenvalue. So let psi subscript n denote some complex eigenfunction, in general complex eigenfunction of some operator A. So the operator acts on the eigenfunction to give the eigenvalue, which I'll call A subscript n, times the eigenfunction back again. Now I'm assuming that this is a discrete index, that it can take the values 0, 1, 2, 3, and possibly infinitely many. If your functions are bounded in space, if they decay to infinity sufficiently rapidly, then you can have eigenfunctions which can be counted. There might be infinitely many of them, but they can be counted with a discrete index. The theory of eigenfunctions which have continuous indices is fun. Please look up the book by Messier called Quantum Mechanics, Volume 1. There's 2 volumes. It will explain how to generalize what I'm doing to continuous indices, but that point is not examinable. This one is though. So here we have an eigenfunction which has a discrete index by assumption. I'm stating without proof that that works fine if these wave functions decay to infinity sufficiently rapidly. So here's our eigenvalue equation. So as postulate number 4, which is written down, I won't flash up the overhead. As postulate number 4, when you measure the dynamical variable A associated with a given quantum system, what you obtain is one of the eigenvalues of the said linear operator. So I'm stating that without proof. Now, if I was teaching mathematics, I'd be telling you about spectral theory. But since I'm teaching quantum mechanics, I'm teaching about the formalism of quantum mechanics. And here's another postulate or another assumption, that when you have an arbitrary operator A, you'll have a set of eigenvalues, A subscript n, little a subscript n. And the claim is, first of all, as a piece of terminology, this set of all eigenvalues of a given linear operator is called the spectrum of that linear operator. And the claim is that when you make a measurement on a given dynamical variable, the measurement that you will get will be one member of the spectrum of the said linear operator. Again, I say that without proof. And that one can't be proved, right? That one can't be proved. That's a physical assumption. The correctness of which, or otherwise, ultimately needs to face the acid test of experiment. We've mentioned earlier the idea of a Hermitian operator. In Dirac notation, a Hermitian operator is an operator, a linear operator A. So you give me any wave function psi, which is sufficiently well behaved to satisfy the Schrödinger equation. You give me a particular linear operator A, then if this is true, for any wave function psi and for a particular linear operator A, then we say that that linear operator A is Hermitian. Remember, this is a triple integral over all space of psi star, the first thing starred, times the second over all space. This is a triple integral of the first thing starred times the second over all space. If these are equal, then the linear operator is said to be Hermitian. And if it's not, then it's not Hermitian. Let me now put a 1 and a 2 subscript on these wave functions. Suppose I was to appear to change the definition and to say, given arbitrary wave functions psi1 and psi2, any pair of such wave functions which is sufficiently well behaved to obey the Schrödinger equation, and a particular linear operator A, then if that linear operator A obeys this, it's Hermitian. Those two definitions look different, but they're in fact equivalent, and I'll ask you in exercise 43 to demonstrate the equivalence of these two different definitions of Hermitian operators, both of which are equivalent to that which we gave earlier. Again, A is a frog, which can hop from the left-hand side of one slot to the left-hand side of another slot and remain unchanged. All right, so this is two different ideas of, or two different notions of the Hermitian nature of an operator. Now, if a given wave function coincides with one of these eigenvalues, then you will always get, when we speak of that wave function as being in an eigenstate of the set operator, and you will always measure that particular associated eigenvalue. For example, you have a plane wave, it has a particular momentum. The plane wave is an eigenvalue, is an eigenfunction of momentum. Momentum operator acts on plane wave to give momentum times the plane wave. When you have a quantum system which is not in an eigenstate of the operator A, then you can get a range of values, the range of values corresponding to the spectrum. Hence postulate 5. Oh, sorry, you can get, start again, please delete that. When a system is not in an eigenstate, then you get the range of possible values drawn from the spectrum of the operator. Postulate 5, the idea that when you have a particular linear operator A, then you make measurements, and those measurements could give a range of values which are drawn from the spectrum of A, but the average measurement, the average value of the linear operator, will be the expectation value of that linear operator, which in Dirac notation is written like this. Now, since the linear operators must be Hermitian, whether they act to the right, this is acting to the right, right? A acts on psi, it's in the right-hand slot. But you could also think of this thing as acting to the left, right? If it acts on the wave function on the left, you have precisely this, but if it's Hermitian, it makes no difference. So there's a certain symmetric notation introduced, where you just sandwich the A between the two sides and you have two vertical lines, but these things mean exactly the same thing. They're equivalent. This second vertical line is slightly confusing. It's introduced because it makes no difference whether you think of that acting to the right or acting to the left. But for now, let's just consider this to be a definition. And the postulate 5 is that when you measure one of the dynamical variables, on average, you'll get the expectation value. I now want to talk about Hermitian conjugation again. And all we're doing here is to take a previous result and to write it in Dirac notation. So you give me a linear operator A, any linear operator A. It acts on some wave function, and you can form this inner product. This is arbitrary well-behaved wave function psi, particular linear operator A. Then by definition, the Hermitian conjugate operator. Now I've written it the other way in the notes. It makes no difference how it's written. Both are correct. If this is not a Hermitian operator anymore, this is a more general object, an arbitrary linear operator. If it hops to the left slot, it picks up a dagger. So arbitrary wave function psi, particular linear operator A. If you move it from one slot to another, it picks up a dagger. And this serves to define the Hermitian conjugate operator A dagger. So this is A dagger. It's also called the Hermitian conjugate operator. Now if A and A dagger are the same, and that's an if A equals A dagger, then that operator is Hermitian. You've seen all this before. This is just written in more compact Dirac notation. If I was giving a mathematics lecture, rather than calling this the Hermitian conjugate operator, I would call it the adjoint operator. So the two words are synonymous, Hermitian conjugate and adjoint. In a quantum lecture, I'll call this a Hermitian operator. I could also call it a self-adjoint operator, one that equals its own adjoint. And there's a couple of rules for adjoint operators in exercise 44. I just want to highlight one of them, that if you consider the Hermitian conjugate of a product of linear operators, you can prove and will prove, and we'll prove in the tute, that it's a product of the Hermitian conjugates with order reversed. We can also have the idea of an inverse operator. You give me some operator A, and I can give you an inverse operator, if it exists, such that A to the minus 1A, or the same thing in the order reversed, equals a unit operator. And the unit operator is just the operator which acts on any wave function to give the wave function again. Lastly, there's a very, very important class of operators known as unitary operators. Very important in mathematics, very important in quantum physics. If, and this is an if, a given operator U, now we're going to reserve the symbol U for operators that are unitary. If the Hermitian conjugate of an operator equals its inverse, then that operator is said to be unitary. So the Hermitian conjugate and the inverse are the same thing. So U dagger is going to be U to the minus 1, which is 1. Or the unit operator is U dagger U or U dagger. So these are unitary operators. These turn out, again, to be hugely important in quantum physics. Two reasons. The growing old operator. Now what's the growing old operator? You give me a wave function at time t equals 0, and you want to ask the question, so this is function of position and t equals 0. You want to apply some operator to it to make it grow old. In the sense of evolving it to some time t greater than 0. There's going to be a unitary operator u, which will depend on t, which can act on the wave function now to evolve it into the future. And an optional earlier exercise had you working this thing out. So time evolution operator, the growing old operator, is an important example of unitary operators. A second important unitary operator is change of representation. This is the wave function written in a representation-free way. It exists, the electron exists independently of how we choose to coordinatize it. It's sort of sitting on the cloud. Yep. Now we could choose to represent the wave function as a complex function of position and time. We could choose to represent the wave function that way. Or we could choose to represent the wave function a different way. For example, psi tilde of k in the Fourier integral equation 15 is another way of representing the wave function. Question, how do you change representations from one arbitrary way of doing quantum physics to a different way? And the answer is you do it with unitary operators. Now we're going to learn how to do that soon, but the point is, a second very important reason for studying unitary operators, as we'll see, is that these things can be used to change representation in quantum physics. Speaking of representations, let me give you a third representation of quantum physics. There's infinitely many of them. We know about this representation, we know about this one. I want to give you a third one, which is called the eigenfunction expansion. This, by the way, might be helpful with a certain assignment question. So eigenfunction expansions. We have the eigenfunctions I mentioned earlier, eigenfunctions of some linear operator capital A, eigenvalues, eigenfunctions again. Let's denote by this set, the set assumed countable, typically countably infinite. Let's denote by this the set of all eigenfunctions of some linear operator A. These are going to be the bricks out of which we build wave functions. You can build walls out of bricks. You can build arbitrary numbers out of powers of 10. With Fourier integrals, you can build wave functions out of sums of plane waves. How about building wave functions out of sums of eigenfunctions, right? So in the Fourier integral, this is the most important thing I'll say all day. In the Fourier integral, we express wave functions as sums of plane waves. Let's be more general than this. Plane waves, by the way, are eigenfunctions of momentum. More generally, you have a set of eigenfunctions for any linear operator A that you can express arbitrary wave functions as sums of those eigenfunctions, and that sum is called an eigenfunction expansion. Instead of adding together a weighted superposition of plane waves, we're now going to add together a weighted superposition of eigenfunctions in our eigenfunction expansion. I've lost my stick. As a loose analogy, you can choose to work out a vector analysis problem in whatever coordinate system you want. You'll choose the coordinate system to make your life as simple as possible, to make the mathematics or the mathematical physics as transparent as possible. There's infinitely many coordinate systems. No coordinate system is privileged. In quantum physics, no representation is privileged. There are infinitely many ways of representing a quantum system. Loose analogy with infinitely many coordinate systems. So let's talk about the eigenfunction expansion. In fact, before we do, let's assume that these eigenfunctions are normalized, which is written in the Dirac notation as follows. Now, before I obtain this eigenfunction expansion, and to remove all possible suspense, it's equation 151, arbitrary wave function. Here's a particular eigenfunction. Let's have some complex weighting coefficient, C subscript n. Let's add them all up, sum over the n, and you'll get the arbitrary wave function. So this is what we're working towards, the eigenfunction expansion, which is equation 151 of the notes. So let's do it. But I need to prove a theorem, and that theorem is that eigenfunctions belonging to different eigenvectors are orthogonal. Notice how, by the way, I'm blurring the language between vectors and functions. Yep. I call this a function, but this is a bunch of numbers, right? You give me that bunch of numbers and I'll represent the function. So I'll call this thing a function because it is. It's a wave function. But you give me that bunch of numbers and I'll tell you what the wave function is. In other words, this bunch of numbers is a way of representing the function. But a bunch of numbers is a vector, right? Functions and vectors, from this perspective, are the same thing. So when I speak of eigenfunctions and eigenvectors, and I'll slip from one language to the other, I'll do so interchangeably for this reason. Functions can be represented as vectors. Linear operators can be represented as matrices, something we've yet to prove. Differential equations, linear differential equations, can be represented via linear equations, matrices acting on vectors. Again, this tight binding, this tight connection between the theory of linear differential equations and the theory of linear algebra, which runs through so much of quantum physics, and today's lecture in particular. So our theorem is that eigenfunctions, so E functions, belonging to different eigenvalues are orthogonal. Again, deliberately geometric language. So we need to prove this. So let's do it. So let's consider some particular linear operator A. Let's consider two distinct eigenfunctions. Two distinct eigenfunctions that I'll call psi I and psi j. Now by assumption, these eigenfunctions are going to have different eigenvalues, hence equation 147. Operator acts on eigenfunction to give eigenvalue that I'll call AI times eigenfunction back again. Similarly for psi j, aj psi j. So these are equations 147. Again, eigenfunctions, they're going to have different eigenvalues. So we're going to assume that AI and aj are different. And with the view of proving this theorem, let me construct the following object. AI minus aj times the inner product, the Dirac product of psi I with psi j. I'm ultimately going to show that this thing equals naught. And having shown that it vanishes by the null factor law, either this must vanish or this must vanish. So let me just cut to the chase. I'm going to prove that this is naught. Hence, by the null factor law, either this must vanish or this one. But we've got, by assumption, different eigenvalues. So by assumption, this is non-zero. Hence, this is 0. Hence, the distinct eigenfunctions are orthogonal. So let's prove this. I'll just expand this out into two terms. AI times a bracket minus aj times a bracket. Next, this is a number. I'm going to bring it inside the first slot of the first bracket, and in doing so it picks up a star. Or I can bring it inside, or I can bring this one inside the right-hand slot, in which case it does not pick up a star. Now I'm going to use the eigenvalue, next. By assumption, these eigenvalues are real. We've already argued for why eigenvalues should be real when we're dealing with quantum mechanical operators. In a purely mathematical setting, A is going to be assumed to be Hermitian, and we already know that that implies real eigenvalues. So this star can be dropped. Now let me use the eigenvalue equation in reverse. AI times psi I is the same as the operator acting on psi I. So I can replace the eigenvalue with the operator. Similarly here, I can replace the eigenvalue with the operator. Next, A is Hermitian. So it's a frog which can hop from here to here without change. When that frog hops, these two terms are now equal, hence this vanishes. Since the eigenvalues are distinct, this must vanish, which is what we wanted to prove, namely that eigenfunctions belonging to distinct eigenvalues are orthogonal. Eigenfunctions which have the same eigenvalues are not necessarily orthogonal, but can be made so via the Graham-Schmidt orthogonalization process. And that's a point that I won't go into. The key point is that we can treat all our eigenfunctions as orthogonal and normalized. Since they're both orthogonal and normalized, deliberately geometric language, then if you were to have the Dirac product of any two eigenfunctions, that will equal 0 if I and j are different, and 1 otherwise, which we represent with the Kronecker delta, which is 0 if the discrete indices are different, and 1 otherwise. So we speak of this as an orthonormal set, which is a conflation of the words orthogonal and normalized. Since they're both orthogonal and normalized, they're orthonormal. Language for vectors, but vectors and functions, the distinction is being blurred here, and deliberately so. So postulate 6, the wave function for a given quantum state can be decomposed as a linear combination of eigenfunctions. That begs the natural question, is this set of eigenfunctions complete? And the answer is yes for bounded quantum systems. but we won't need to prove this. Complete means, can I build any brick wall out of a set of bricks? Yes, if I've got a complete set of bricks. Can I express an arbitrary wave function as a superposition of such eigenfunctions? If the answer is yes, then by definition the set is complete. We won't prove completeness here. If you want to see that completeness proved, then look up a book on axiomatic quantum mechanics. So we have this blurring of a function, psi of RT, and then this bunch of numbers, these coefficients, C for coefficient, which weights each eigenfunction in the eigenfunction expansion. That begs the obvious question, how do you get the C's? Now, if this was an arbitrary vector, right, and this was a sum of unit vectors, then you'd be asking the question, this arbitrary vector is going to be some number, I don't know, C subscript x times the x unit vector, plus another coefficient, let's say C subscript y, times the y unit vector, plus C subscript z times the z unit vector. So these coefficients are going to be would be components of a vector if we were talking about decomposing a vector. If you're talking about decomposing an arbitrary vector v, then you'd be saying that this is the projection of the vector v onto the unit vector. This will be the projection of the vector v onto the unit vector, and so on. So we can sort of begin to think of these coefficients in the eigenfunction expansion as coefficients, or sorry, projections of the function in the direction, in inverted commas, of the eigenfunction. But we need to work out what these coefficients are, and we should expect it to be like a dot product. In fact, it should probably be an inner product between the thing you're decomposing, the wave function, and the unit vector. So we expect something to look like an inner product of the wave function. So are these the coefficients, the projection, the dot product in inverted commas, of the thing you're decomposing and the thing you're decomposing it over? The answer is going to be yes, except these are around the wrong way. But we need to prove this, so let's do it. What are the coefficients C in the eigenfunction expansion? So I'm going to begin by just writing down the eigenfunction expansion with some judicious gaps. So sum over n's of Cn and our eigenfunctions. Now this thing has motivated the idea that we need to take our function and project it onto, in inverted commas, the eigenfunction. So let's do that. Let's project our function onto a given eigenfunction. Now, I could write an n subscript, but I'd be bad because that n has been summed over here. So let me give this a different name. Little psi subscript n. We're projecting the wave function using geometric language onto a given eigenfunction. And what I do to the left-hand side, I do to the right-hand side. Now, the act of taking a dot product, or the act of taking a Dirac bracket, is linear. So this sum can come out the front. This right-hand side had no stars, and so the Cn comes out with no star. This object, we're going to consider our eigenfunctions to be both orthogonal and normalised. So this is a Kronecker delta with m and n subscripts. This, by the way, is a discrete analogue of the Dirac delta. Any integral involving the Dirac delta is trivial. You throw away the integral sign, throw away the Dirac delta, etc. Here we have the Kronecker delta, the discrete form of the Dirac delta. Any sum involving the Dirac delta is trivial. You throw away the sum, you throw away the Dirac delta, what's left, and you evaluate it when these are equal, m equals n. Stated differently, this thing is only ever going to switch on. This thing will only ever be non-zero when the running index n happens to equal m. So every term gets killed off except when n equals m, in which case this is 1 and this is C subscript m. Hence, C subscript n, the coefficients that we wanted, precisely this thing, the projection of the wave function onto the eigenvalue, direct geometric analogue of this. So, when we write down our eigenfunction expansion, arbitrary wave function, coefficients Cn, eigenfunctions psi m, then these coefficients Cm can be written using this formula here as follows, and then the wave function back again. So this is the eigenfunction expansion, and this is how we get the coefficients. And what I've just written down is equations 153 and 154 in the notes. Again, this very, very strong geometric interpretation. I've just sketched it, but at this point your head should be ringing, light bulbs should be going off in your head, because you learned so much about linear algebra in your undergraduate courses. You also learned so much about differential equations in your courses. Now, sure, I'm connecting the two for the purposes of quantum physics, but that connection is much, much, much more general. This connection between a function and a vector, that's what this connection is. That's a function, and the vector is a bunch of numbers, right? Differential operators we're going to show in a later class to be matrices. This connection between linear differential equations and linear algebra is profound and deep. It doesn't just run through quantum physics, it runs through signals engineering, physical optics, communications engineering, general relativity, gravitational waves, you name it. This connection is very, very strong and very, very deep. Pioneered primarily, by the way, by rational mathematicians. I'll stop there. Thank you.